Picture a standard 24-hour clock. Let that dial represent the entire 4.6 billion year history of Earth, starting from the violent moment our planet formed at midnight, right up to the exact second you are watching this video. If you are looking for the historical landmarks we all know, you'll be waiting a while. Dinosaurs don't even show up until about 11 p.m. Humans? We are the final few seconds before midnight. We are practically a rounding error on this clock. Today, we are completely ignoring that final hour. We are going to look strictly at the first 23 hours. This is the Precambrian era. It covers roughly 88% of Earth's timeline. History books usually skip this era entirely because evidence is hard to find. Earth is a highly active planet. It constantly recycles its crust like a giant conveyor belt, pushing ancient rock deep underground and melting it back into magma. The library is constantly burning itself down. The chapters that did survive tell a violent story. Right out of the gate, Earth was slammed by a Mars-sized planet. The sheer energy of that impact vaporized massive portions of the rock itself, leaving behind a churning, toxic ocean of magma. For decades, geologists assumed the planet stayed a molten hellscape for hundreds of millions of years. But tiny, nearly indestructible crystals called zircons tell a different story. The chemical signatures trapped inside these microscopic time capsules show they formed in liquid water. Just 150 million years after the planet coalesced, the crust cooled enough for massive, high-pressure oceans to form. The oceans provided the physical medium, the hardware, but the atmosphere above it was incredibly dense and lethal. To build a world that could actually sustain complex organisms, biology had to write a brand new operating system from scratch. 4 billion years ago, the sun was roughly 30% dimmer than it is today. Based on standard astrophysics, a sun that weak should have left the early Earth completely frozen over. The planet stayed warm thanks to microscopic, single-celled organisms. These early microbes thrived in the oxygen-free oceans, and as they metabolized energy, they pumped out massive amounts of methane gas. Methane traps heat incredibly well, creating a powerful greenhouse effect. High in the atmosphere, that methane reacted with sunlight to form a thick, organic smog. If you looked up, the sky wasn't blue. It was a hazy, glowing orange. This blanket trapped the heat, and it acted as a chemical shield, blocking lethal ultraviolet radiation from reaching the surface. Life was keeping the planet perfectly warm. Then, cyanobacteria figured out how to use sunlight to split water molecules for energy. As they built the sticky, layered microbial communities we now see fossilized as stromatolites, they started releasing a highly reactive metabolic byproduct, free oxygen. The early oceans were packed with invisible, dissolved iron. As soon as cyanobacteria puffed out a molecule of oxygen, it violently reacted with that iron, turning it into solid rust. For hundreds of millions of years, this iron oxide rained down to the ocean floor, forming the massive alternating bands of red iron and gray silica you see preserved in the rock record today. Eventually, the ocean's chemical sponge got full. With no more dissolved iron, free oxygen bubbled up and flooded the atmosphere. It immediately reacted with the methane blanket, stripping it away and replacing it with much weaker carbon dioxide. By pulling off the planet's heavy thermal blanket, this biological innovation poisoned its own environment and broke the planetary thermostat. The global temperature plummeted, and Earth plunged into its first snowball Earth event. Volcanic activity eventually built up enough greenhouse gas to melt the ice, leaving behind a brand new ozone layer. The planet stabilized, forming a single massive supercontinent. And then, for nearly 1 billion years, geology simply stopped doing anything interesting. This stability hindered evolution. The deep ocean layers became stagnant and packed with hydrogen sulfide gas. This sulfur bound tightly to trace metals like copper, zinc, and iron, pulling them down into the deep mud. The ocean ran out of the metallic building blocks needed to construct advanced enzymes, creating a nutritional plateau that lasted 1 billion years. Trapped in this nutritional wasteland, single-celled life turned inward. Simple cells swallowed other cells, forming permanent internal partnerships to generate energy. These complex eukaryotic cells eventually started shuffling their genetic code every generation through sexual reproduction, rapidly accelerating their ability to adapt to a harsh environment. Just as eukaryotic partnerships and sexual reproduction began rewriting the biological code, the stagnant supercontinent broke apart directly over the equator. Relentless tropical rain battered the newly exposed rock. This caused intense chemical weathering, a reaction that physically sucked carbon dioxide straight out of the atmosphere and locked it away in the ocean floor. The atmosphere lost its greenhouse heat once again. Ice caps formed at the poles. Because bright white ice reflects incoming sunlight rather than absorbing it, the cooling accelerated. The ice crept further and further down the latitudes until the entire planet snapped into a frozen, solid white sphere. Life was brutally compressed into tiny, disconnected safe zones near underwater volcanoes or slushy meltwater pools. This extreme geographic isolation acted as an evolutionary pressure cooker, forcing the survivors to adapt or die out entirely. Plate tectonics kept grinding under the ice, volcanoes continuously pumping out carbon dioxide, eventually overpowered the global ice. As the glaciers aggressively melted, they washed a massive fertilizer dump of rock dust into the oceans. This nutrient flush fueled incredible biological growth. The shallow seafloors were soon covered in thick, leathery microbial mats. Lying peacefully on top of these mats were huge, soft-bodied organisms absorbing nutrients right through their skin. No teeth, no hard shells, no predators. But a new type of animal was about to ruin the neighborhood. Symmetrical, worm-like organisms developed the musculature to aggressively dig down into the mud, rather than just politely sitting on the surface. This burrowing behavior shredded the fragile microbial mats. The flat, peaceful garden turned into a chaotic, three-dimensional mud pit. Animals started actively hunting each other, forcing prey to rapidly evolve hard calcium skeletons and defensive shells just to survive. Today, we look at the stars, hunting for Earth-like planets that might support biology. But for 88% of our own history, Earth-like meant a toxic orange smog or a ball of ice. We must realize that life is a geological force that engineered the blue sky we now take for granted.